Dr. M. P. Jayaraman is an assistant professor in mathematics in L.N. Government College, Poneri. He has specialized on geometric function theory. With 14 years of teaching experience, he has handled topics on probability and queuing theory, discrete mathematics, random process, and engineering mathematics. Being a recognized supervisor for guiding PhD and MS students of Anna University, he is the reviewer of the journal Computer Mathematics and Applications. He has also written books on discrete mathematics and has also published papers in 28 international publications, in 4 national publications, and has presented papers in 2 international and in 2 national conferences.
Welcome you all for UGC lecture series in mathematics. In today's session, we are going to discuss about Wolf algorithm to solve a quadratic programming problem. The idea about Wolf's algorithm is, first we will try to derive the Hundecker condition from the given quadratic programming problem. Then by introducing a new objective function, we will convert the given quadratic programming problem into linear programming problem. Finally, we are going to solve the modified linear programming problem using two-phase simplex method. The first steps of Wolf's algorithm is convert the inequality constraints into equation by introducing the slack variable Si squared in the ith constraint. I values varies from 1 to m, and the slack variable Smj squared in the jth non-negativity constraints j equal to 1 to n. So, the first step is we convert the inequality constraints into equation by introducing slack variable in the given set of constraints and non-negative constraints. Step 2 is construct the Lagrangian function for the given quadratic programming problem, where Lagrangian function L is this equation summation Cij xj j varies from 1 to n plus of double summation Cij xj xk. This equation corresponds to the given objective function minus summation lambda into summation Aj xj minus Bi plus Si squared. This equation corresponds to the given set of constraints and minus summation j equal to 1 to m lambda mj into minus xj plus s squared mj, and this set of equation corresponds to given set of non-negative restrictions. So, construct Lagrangian function for the given quadratic programming problem, which we displayed here. Now, differentiate this Lagrangian function partially with respect to the decision variable x, s and lambda, and equate the first order partial derivative equal to 0. We derive the Hundecker condition. So, step 2 in Wolf's algorithm is construct the Lagrangian function for a given quadratic programming problem and go for partial derivative of the Lagrangian function with respect to x, s and lambda and equate to 0 and try to derive the Hundecker condition. The third step of Wolf's algorithm is introduce a non-negative artificial variable Wj, j varies from 1 to n in the Hundecker condition, which we written as Cj plus summation Cjk xk minus summation lambda I aij plus lambda m plus j equal to 0 for j equal to 1 to n, and construct an objective function z equal to w1 plus w2 etc. wm. So, the third step of Wolf algorithm is introduce a non-negative artificial variables in the Hundecker conditions and construct a new objective functions. And the fourth step of Wolf's algorithm is obtain initial basic feasible solution to the modified LPP. So, obtain an initial basic feasible solution IBFS to the LPP, which has a new objective function maximize z equal to w1 plus w2 etc. wn subject to the set of constraints. where our x n plus I equal to s I square, I varies from 1 to m, and the important one is this LPP should satisfy the complementary slackness condition summation lambda I s I squared equal to plus summation x j mu j equal to 0. So, fourth step of Wolf algorithm is obtain initial basic feasible solution to the LPP. The fifth step is use two-phase simplex method, and obtain optimum solution to the given LPP of the LPP obtained in step 4. So, for an LPP obtained in step 4, by applying two-phase simplex method, we will try to get the optimum solution, and the solution should satisfy the complementary slackness conditions. So, step 5 of Wolf's method is by applying two-phase method, we try to obtain the optimum solution of the given LPP, which should satisfy the complementary slackness condition. And the final steps of Wolf algorithm is the optimum solution obtained in step 5 is an optimum solution to the given quadratic programming problem. So, by making use of two-phase simplex method, we obtain optimum solution to the given LPP, which satisfies the complementary slackness condition. That solution is the optimum solution to the given quadratic programming problem. So, in Wolf algorithm, first we will obtain Hundaker condition for the given quadratic programming problem. Then by introducing new objective function, we will convert the given QPP into a linear programming problem. Then by applying two-phase simplex method, we obtain solution to the given modified linear programming problem, which satisfies the complementary slackness condition. That solution is the optimum solution of the given quadratic programming problem. Now, by applying this Wolf's algorithm to a given quadratic programming problem, we try to obtain optimal solution to the given QPP. Problem is use Wolf's method to solve the given quadratic programming problem, which maximize z equal to 4 x 1 plus 6 x 2 minus 2 x 1 squared minus 2 x 1 x 2 minus 2 x 2 square, subject to the constraints x 1 plus 2 x 2 less than or equal to 2. Of course, the non-negative constraints x 1 x 2 greater than or equal to 0. So, the given problem involving two decision variable with a constraint with a non-negative restriction. Now, the first steps in Wolf's method is by introducing slack variable, convert the inequality constraints into equation constraints. So, if we consider this constraints, by introducing the slack variable, we can rewrite this inequation as equation, which is x 1 plus 2 x 2 minus s 1 squared equal to 2, where s 1 squared is plus s 1 squared equal to 2, where s 1 squared is the slack variable. Now, the first non-negative constraint is x 1 greater than or equal to 0. We rewrite this as minus x 1 less than or equal to 0. Now, by introducing slack variable to this inequation, we will write this non-negative restriction as minus x 1 plus r 1 squared equal to 0. By taking x 2 greater than or equal to 0, again by introducing a slack variable, we rewrite this equation as minus x 2 plus r 2 squared equal to 0. So, by introducing slack variable in the given set of constraints and the non-negative restriction, we can rewrite the inequality constraint into equation constraint by introducing slack variable. Therefore, the given problem can be rewritten as maximize z equal to 4 x 1 plus 6 x 2 minus 2 x 1 squared minus 2 x 1 x 2 minus 2 x 2 squared, subject to the constraints x 1 plus 2 x 2 plus s 1 squared equal to 2 minus x 1 plus r 1 squared equal to 0 minus x 2 plus r 2 squared equal to 0. Of course, x 1 x 2 s 1 squared r 1 squared r 2 squared, all the variables takes a non-negative value. Now, from this equation, we will try to obtain Lagrangian function, where Lagrangian function L is the objective function minus lambda 1 into first set of constraints minus mu 1 into second constraints minus mu 2 into third constraints, which we displayed as a Lagrangian function. So, for the given problem, the Lagrangian function is the objective function minus lambda 1 into first constraints minus mu 1 into the first non-negative restriction minus mu 2 into second non-restrictive condition. In order to derive the Hundaker condition for the given problem from this Lagrangian function by differentiating L partially with respect to x 1, x 2, s 1, lambda 1 and mu 1, mu 2, r 1, r 2 will get set of equations. So, go for partial derivative of L with respect to x 1 and equate to 0, we will get it as 4 minus 4 x 1 square minus 2 x 2 minus lambda 1 plus mu 1 equal to 0. So, the partial derivative of L with respect to x 2 and by equating 0 we will get as 6 minus 2 x 1 minus 4 x 2 plus 2 lambda 1 plus mu 2 equal to 0. Now, the partial derivative of L with respect to lambda 1 gives us minus of x 1 plus 2 x 2 plus s 1 square minus 2 equal to 0. Now, the partial derivative of L with respect to s 1 gives us minus 2 lambda 1 s 1 equal to 0. Now, partial derivative of L with respect to mu 1 gives us minus of x 1 plus r 1 square equal to 0. The partial derivative of this function L with respect to mu 2 gives us minus of x 2 plus r 2 square equal to 0. Now, the partial derivative of this function L with respect to r 1 gives us minus 2 mu 1 r 1 equal to 0. Similarly, partial derivative of L with respect to r 2 gives us minus 2 mu 2 r 2 equal to 0. So, from the Lagrangian function, the partial derivative of L with respect to x 1 x 2 gives us equation 1 and 2 and partial derivative of L with respect to lambda 1 gives us equation 3 and partial derivative of L with respect to s 1 is equation 4. Partial derivative of L with respect to mu 1 is 5, mu 2 is equation 6 and partial derivative of L with respect to r 1 is 7 and this one is 8. Now, we try to simplify this equation. From the equation 1, we will rewrite it as 4 x 1 square plus 2 x 2 plus lambda 1 minus mu 1 equal to 4. From equation 2, we have 2 x 1 plus 4 x 2 minus 2 lambda 1 minus mu 2 equal to 6. From equation 3, we have x 1 plus 2 x 2 plus s 1 squared equal to 2. Now, from equation 4, we have lambda 1 s 1 equal to 0. Now, we try to simplify equation 5, 6, 7 and 8. From equation 5, we have our x 1 value is r 1 square. Therefore, using equation 5 in 7, equation 7 can be written as mu 1 into x 1 equal to 0. Now, using equation 6 in equation 8, equation 8 can be written as mu 2 x 2 equal to 0. So, from this equation, by making use of equation 4, 5 and 7, 8, we get these two equations. So, from the Lagrangian function, by making partial derivative of L with respect to decision variable and by simplifying those equations, we get the equation as 4 x 1 square plus 2 x 2 plus lambda 1 minus mu 1 equal to 4, 2 x 1 plus 4 x 2 minus 2 lambda 1 minus mu 2 equal to 6, x 1 plus 2 x 2 plus s 1 square equal to 2 and lambda 1 s 1 equal to 0, mu 1 x 1 equal to 0, mu 2 x 2 equal to 0. Let us have a break. Welcome back. Before break, we discussed about the algorithm of Wolf's to solve a QPP. Now, with the help of this Wolf's algorithm, we try to solve the given quadratic programming problem. So, from the Lagrangian function, we get this set of equation where the first equation is 4x1 squared plus 2x2 plus lambda 1 minus mu 1 equal to 4. Second equation is 2x1 plus 4x2 minus 2 lambda 1 minus mu 2 equal to 6. And third equation x1 plus 2x2 plus s1 squared equal to 2, and lambda 1 s1 equal to 0, mu 1 x1 equal to 0, mu 2 x2 equal to 0. Now, this set of equation lambda 1 s1 equal to 0, mu 1 x1 equal to 0, mu 2 x2 equal to 0 is called complementary slackness condition. Complementary slackness conditions. Here our variable decision variable x1 x2, lambda 1 lambda 2 and s1 all are greater than or equal to 0. So, for a given quadratic programming problem, with the help of Lagrangian function, we derive the Hundaker condition as this one. So, the given problem can be rewritten as in this form, where we introduce a new objective function z star equal to minus a1 minus a2. So, from the Hundaker condition, by introducing an artificial variable, we modified the given LPP in which the objective function z star equal to minus a1 minus a2, subject to the constraints 4x1 plus 2x2 plus lambda 1 minus mu 1 plus a1 equal to 4, and second set of constraint is 2x1 plus 4x2 plus 2 lambda 1 minus mu 2 plus a2 equal to 6, and the third equation is x1 plus 2x2 plus s1 squared equal to 2, which satisfies the complementary slackness condition lambda 1 s1 equal to 0, mu 1 x1 equal to mu 2 x2 equal to 0, where x1 x2 lambda 1 mu 1 mu 2 a1 a2 are greater than or equal to 0. So, here we are introducing the artificial variable in the first set of constraints and second set of constraints in order to get the initial basis matrix. So, by introducing artificial variables, the LPP is modified in the following form, in which z star equal to minus a1 a2 subject to the constraints this set of equation. From this equation, we will get the initial basic feasible solution. So, for the given LPP, the initial basic feasible solution is 1 0 0 0 1 0 0 0 1, and the variable is a1 a2 and s1 equal to 4 6 2. So, from the modified LPP, we can write the initial basic feasible solution as this form. From this, we can get our initial basic feasible solution as a1 equal to 4 and a2 equal to 6 and s1 equal to 2. So, from the modified linear programming problem, we will get the initial basic feasible solution as this one, a1 equal to 4, a2 equal to 6 and s1 equal to 2. Now, for this linear programming problem, by applying two-phase simplex method, we can get the optimal solution, wherein which each and every iteration we are improving our optimal solution from the initial basic feasible solutions. Now, we will form a simplex table for the given set of LPP. Now, our linear programming problem involving these three set of constraints. So, first simplex table is CB, the second one is YB and third one is XB, where YB is the basic variable, YB is basic variables. As far as this problem concerned, we have basic variable as A1, A2, S1, and CB is the cost for the corresponding basic variable. So, CB is the cost of basic variable, and XB is the initial basic feasible solution. So, for this problem xb is the solution, xb is the solution of the basic variable. So, the next column is we have two decision variable y1 and y2, then we have a variable lambda 1, mu 1 and mu 2, then we introduce two artificial variable a1, a2 and slack variable s1. So, our simplex table involves basic variable yb, cost of the basic variable and solution of the basic variable. So, for this set of constraints our basic variables are a1, a2 and s1. The cost for a1 is -1, the cost of the basic variable a2 is -1 and for the all other variable the cost is 0. Therefore, CB for the YB of a1 is -1, a2 is -1, s1 is 0. Now, the solution is for the a1 the solution is 4, a2 6 and s1 2. Now, this table if we consider the first set of constraints, that is 4x1 plus 2x2 plus lambda 1 minus mu 1 plus a1 equal to 4, our y1 value is 4, y2 value is 2, lambda 1 the coefficient is 1, mu 1 the coefficient is -1, there is no mu 2 therefore 0, and a1 the coefficient is 1, there is no a2 0, there is no s1 0. So, by taking the coefficient of the first constraints we will get the value as 4 2 1 -1 0 1 0 0. Now, consider the second constraints 2x1 plus 4x2 plus 2 lambda 1 minus mu 2 plus a2 equal to 6. We have the values as 2 for y1, 4 y2, for lambda 1 2, there is no mu 1 therefore 0, for mu 2 the coefficient is -1, there is no a1 coefficient 0, for a2 the coefficient is 1, there is no s1 0. In a similar way, for the third set of constraints we have the term as coefficient of x1 is 1 2, there is no lambda 1, there is no mu 1, there is no mu 2 and a1 coefficient 0, a2 coefficient 0 1. So, the table is nothing but simplex table. We obtain the simplex table from the given set of LPP, linear programming problem. From this simplex table, each and every time we try to improve the optimum solution. In order to get the optimum solution, we have to check the condition that all Zj minus Cj value should be greater than or equal to 0. If all Zj minus Cj greater than or equal to 0, then optimal solution to the given linear programming problem is obtained. So, for this simplex table, first we have to check all Zj minus Cj value greater than or equal to 0. So, Zj is summation Cbyj, then Zj minus Cj is summation Cbyj minus Cj. So, for this table first we have to compute Zj value, then Cj value, then Zj minus Cj. Zj is Cbyj. So, for this one Zj Cj. For this table, suppose for y1 my Zj value is -1 into 4 plus -1 into 2, Cb1 y1 plus Cb2 y2. So, -1 into 4 that is -4 plus -1 into 2 that is -2. So, -4 minus 2 we will get it as -6. In the same way, for y2 my Zj value is -1 into 2 plus -1 into 4 which is also -6. Then for lambda 1 -1 into 1 plus -1 into 2, so which gives us -3. Then for mu 1 -1 into -1 which is +1. Then for mu 2 -1 into 0 plus -1 into -1 which we get it as 1. Then in this table a1, a2, s1 are the basic variables which appears in the basis. Therefore, for this basic variable a1, a2, s1 our Zj minus Cj value is always 0. Therefore, no need to compute this Zj and Cj and Z minus Cj for the basic variables, because for basic variables Zj minus Cj values are 0. Now, the cost of the variable x1 is 0, cost of x2 is 0, lambda 1 0, mu 1 0, mu 2 0. So, from this we will get Zj minus Cj as for y1 minus 6, y2 minus 6, lambda 1 minus 3, mu 1 1, mu 2 1. Now, in this table, if all Zj minus Cj greater than or equal to 0, then optimum solution is obtained. But for this problem, not all Zj minus Cj is greater than or equal to 0, because Z1 minus C1 is minus 6, Z2 minus C2 is minus 6, Z3 minus C3 is minus 3. Since not all Zj minus Cj greater than or equal to 0, optimum solution is not obtained. Now, we try to improve the optimum solution to the given problem, which we will discuss in the next session. Let me sum up the Wolff's algorithm. The first step of Wolff's algorithm is, for the given quadratic programming problem, derive the Hundecker conditions. So, the first step of Wolff's algorithm is derive Hundecker condition for the given quadratic programming problem. The next idea is introduce a non-negative artificial variable in the Hundecker condition and construct the new objective function. So, step 2 of Wolff's algorithm is, by introducing a non-negative artificial variable in the Hundecker condition, construct a new objective functions. Obtain initial basic feasible solution to the given LPP is our third step of the Wolff's algorithm. After obtaining initial basic feasible solution, by applying two-phase simplex method, try to get the optimal solution to the given problem. That solution should satisfy the complementary slackness conditions. So, the optimal solution which satisfies the complementary slackness condition is the optimal solution to the given quadratic programming problem. Thank you.